Hi everyone, here now we will go through the solution for homework for the last week about tree-based models. So for this homework, we needed to work on New York City Airbnb open dataset, the same one we used in 2 previous homeworks. So let me download it. So first I will download the notebook starter. So I first need to go to this directory. So I already have Jupyter right here. So I want to download the notebook starter. Okay, so I have it here, and then I also want to download the dataset. So okay, I download it. Now let me open it. Okay, so this is the notebook starter. So here what we need to do is we need the goal of this homework is create a tree-based regression model for predicting apartment price. So let me just run it. So I always have this warning. Okay, so now we are reading the data set. Is that file is not found? So let me check that. Okay, I didn't download the file. So now it should be fine. Okay, let me execute it one more time. So okay, now we loaded the data. And now what we need to do is to apply the log transformation to price, then do train validation test split with the usual 60-20-20 distribution. And for that, we use train test split. And I already have the notebook here that we used for the lectures. So let me just scroll a bit. So we're interested in this part that we'll use for splitting. So let me just copy it here and use one here. Then I'll copy this part as well. So we'll reset the index and then let me just copy everything. Then deleting this as well. So here our target variable is not status but price. So let me replace it. And then so the actual the target value in our case will be price. Then I take values and then we apply the logarithmic transformation. So this log 1p. And let me copy it here. And instead of data frame train, we have data frame validation in data frame test. So this should work, hopefully. So let's take a look. Yeah. So it looks correct. So now we did this, we split the data. And the next step is we need to use dictionary vectorizer to turn train and validation datasets into matrices. So for that, first we will turn the data frames into dictionaries. So train dictionaries will be, so let me take this list of columns. I'll put it here and remove price. So we have all these features that we want to use except price. Then I'll take data frame train, then list of these features, and then I'll use the function to dictionaries. and records. I'll do the same for validation. Just to check if it's working. Yeah, it seems to work. So validation. Yeah, okay. So we did that, and then the next step, what we need to do is we need to use the dictionary vectorizer to turn in train and validation data set into matrices. So from scikit-learn, feature extraction, import dictionary vectorizer, and then now we create dictionary vectorizer. Then xtrain would be fit transform train dictionaries. And next validation will be just transform. Type here transform. So the shape of our xtrain matrix and x validation matrix. So this is the shape, yes. Okay, let me delete this. So now we did everything we needed. And now we need to answer the first question. So the first question is, so let's train a decision tree regressor to predict the price variable. We need to train it with parameter max depth 1. Then we need to answer this question: which feature is used for splitting the data in this decision tree? So let's first train a decision tree regressor. So from scikit-learn, trees, import decision tree. I think it's tree, not trees, decision trees. And in lectures, we use decision tree classifier, but here we need regressor. So we have a regressor, and decision tree regressor, and then we use this max depth parameter of 1. And then we feed it. We use xtrain, ytrain. So this is our model. And what we need to do now is we need to use this, remember here, we visualized the tree. We use this export text. Let me copy it here. And what I also want to do is import this export text. Now let's just visualize it. And we see that the feature we used for splitting the data was room type for some specific type of room, entire home or apartment. So the decision tree we have here is, if it's not the entire home or apartment, then the price is this. So it will predict, let me draw it. So this is the decision, the condition node we have, which is room type, this entire home apartment. And then we have two nodes, two decisions. So in case it's yes, and we predict what was that? No, in case it's yes, we predict 515. 515. And in case it's no, we predict it's 429. Was it 9? Yes, 429. So this is a very simple decision tree. Among all the features, it looks as just this one, and then it makes a prediction. So if this is an entire house, then this is the price it predicts. Otherwise, this is that price. So a very simple decision tree. So the correct answer here is room type. So this is because this is the feature that is used for splitting the data. Then question 2 was train a random forest model with these parameters. So yes, so what we need to do now is import decision tree random forest regressor. So ensemble package, import random forest. So again, we have classifier and regressor. We're interested in regressor. And let's create this random forest regressor. I will copy these things from here. So we train 10 estimators. We fix the random seed, and we all want to use all the available CPU cores. So fit again x train y train. Okay, and now let's use it. Random forest predict. So because this is a regressor, not the classifier, we don't have predict proba, we only have predict. And here we use y predation to get predictions. So these are predictions, y pred. Now we need to evaluate the quality of this model. So we need to compute the RMSE. So for that, we import RMSE from the metrics package. Root. So mean squared error, I think. It's mean squared error. Yes. And now we use this mean squared error. So we compare this y true, which is in our case y validation, and y prediction. And this is not squared yet, so we need to square it. SQRT. And this is what we get. So it's a little bit different. Yeah, so basically this should be this answer. And the reason it's a bit different is because I prepared this homework on a different computer. So I think this is why it's slightly off. But yeah, this is still the closest one. Let me also write the answer here. Answer. Okay, so then we have the next question is we get our random forest and we experiment with number of estimators parameter. So let me copy this part. So what we want to do now is we want to iterate over different parameters in a range from 10 to 201 with step of 10. And then let's call it not I, but N. So the number of estimators here would be N. Random state we set to 1. And then we fit the model. And then what we want to do is we want to evaluate this model. So just put this together. So this would be score. And then let's have scores. And now we will append to this list of scores. Append. So we'll append the number of estimators and the actual score. And then we'll create a data frame. So it's very similar to what we did in the lectures. Scores and then columns will be, so first we have number of estimators. and then RMS here. Right. Then what I also want to do here is I want to use TQDM to watch the progress. TQDM. So I'll just put TQDM here. Okay, let's train it. So it takes a while because we need to train this random forest regressor for more and more estimators. So that's why each next iteration takes more than the previous one. So while it's training, I will already will write some code for plotting. So from the scores, data frame scores and estimators will be our x-axis, and then data frame scores RMSE will be our y-axis. So just execute that. So the question we have here in this for question 3 is at which point RMSE stop improving. So at which point it doesn't make sense to add more trees. So for doing that, we will plot this RMSE value against number of estimators, and we will see when it will stop improving. Okay, so the last one. Okay, it's ready. Something is wrong. Let's see. So let me take a look at. Okay, I have an error here. So actually, I need to append score, not scores. Okay, I will have to wait for 1 more minute. So I hope this time it will. I think it's taken faster, like it's faster now. Not sure. Okay, let me see what we have next after this question. So in the next question, we will be experimenting with max depth parameter. And we will also try different values of n estimators. Okay. Yeah, I will see you. I will actually show you how to make it a bit faster. So now we will do this and I will show you how to make it faster. Maybe just after this finishes. Okay, I think it was slightly faster. Maybe it took 10 seconds less. Okay, let's plot it. And so what we see here is that like at some point it kind of reaches a plateau. So it doesn't really improve. I mean, it does go down a little bit, but only a tiny bit. So it is, as we see, like first, when let's say for first 25, it goes down very fast, right? Then for the next 50, like already the slope is not that steep. So yeah, and then for the next 25, it's even less steep, and then it's less and less and less steep, and at some point it goes to plateau, like it stops improving. Like it does improve, but only little bit. And I think actually like around maybe like around this 150 for sure, like it improves, but only a tiny bit. And yeah, so I think somewhere around 120 yeah, like there are some improvements, but I like it's really like it's not really improving, like only just a little bit. So that's why. Of course, this question may be ambiguous. So you can say, okay, it stops improving after this one. So that's why I only put here 120, which like here, it's kind of clear that after 120, it doesn't improve. Like if, let's say, if you compare it to 70 here. So after 70, it's still improving, but in my opinion, after 120, that doesn't. So yeah. Another way of checking this, maybe let's round it a little bit. So we can round it using, I don't know, 3 digits, for example. So yeah, we see that it dropped a little bit. Yeah, maybe rounding is not a good idea because yeah, it just rounded down. But yep, we can see that here around 120. It did maybe a little bit improved here, but yeah, not significant compared to improvements over here. So that's why the answer here is this. And then I promised to show like how to make it faster. Because if you think about this, so what we were doing here is so we were fitting. So here, let's say for first 25, so we were fitting the first 25 trees, and then because we were moving in 10 steps. So what I'm trying to say is like when we train this, when we train random forest. So let's say, so we train our first tree, right? And we train our second tree, and so on. We have 10 trees, right? And this is our first model here. So this is our first iteration. We train 10 models. And then what we do next is, so this is first model, right? So then our second model is we take this and we train one more group of trees. So we train tree 11, we train tree 12, and we train tree number 20, right? And this part here and this part here are the same. Right? And then for the third iteration, we again take what we already have. We take that and we just add another bunch of trees here. So we added 3, 21, 22, and this is 30, right? So this part, so this is third iteration. So this part here and this part here, they are the same. So we're basically doing the same thing over and over again. And there is a way to avoid this. So let's say we, on the first iteration, we compute this part, then remove that. And then for the second iteration, we compute only this part and we reuse the first part already computed. And then here we just train this more trees on top of that, and this is already computed. So we don't need to do this work every time again, starting from scratch. And for doing this, let me copy this. So there is a parameter in random forest. It's called worm start. So it's just find it. It's worm start. Yes. And the default file. Let's check what the document says. What the doc says. So the doc says from worm start. Where is it? Okay. Worm start. Okay. When set to true, reuse the solution of the previous call to fit and add more estimators to the ensemble. And if it's false, we train a whole new forest. So here we don't want to train a whole new forest. We just want to reuse the solution for the previous call to fit and add more estimators to the ensemble. So that's why we use worm start true. I don't know if it will work here and estimators 0. But here at each iteration, we will increase the number of estimators. And for doing this, we will just, so there is a field called n estimators, and we will just set it to n, and we will invoke this fit method over and over again on the same instance of random forest model. So here we will basically do that. So at each iteration, we will add new bunch of trees, and we will reuse what is already trained. So let's see. Yeah, and this training goes a lot faster because now we don't need to train everything from scratch. We just add 10 more trees at each iteration. So let me copy this plot. And as you see, the solution is the same one. And because we've fixed the random state, the random seed, then the trees that we get when we do it this way, they're the same trees basically. Okay, so I already showed you the answer, and then I showed you how to use this worm start parameter. And then the next question we have is we want to select the best max depth parameter. So for that, we want to try different values of max depth. And also for each of these values, we want to try different number of estimators because we want to see like at which number of estimators we need to stop, like when we need to stop training more models, and we fix the random seed. So let me copy this. And so we will have a loop here for let's have TQDM here as well. 10, 15, 20, 25. Yes, I think so. Then here we set the max depth. So we use random state 1. We keep n jobs at -1. Yeah. And here we also append this d max depth. So let me add it here as well. Max depth. So it just looks nicer. Okay, I hope I didn't make any errors here. Let's see. So now we're training the first random forest with depth of 10. So now we're training the second one. It's a bit faster actually. Not sure why, because the first one is actually smaller. Yeah, so now we're trying 20, and the next one will be 25. Okay, so we almost finished. Okay, it's done now. So let's check what is inside df scores. Yeah, this is our data frame with scores. So now let's plot it. So I'll copy this thing. So we don't need TQDM here anymore. Then data frame subset. So it's data frame scores, and then we filter on max depth equals to D, and then we plot have number of estimators on the x-axis, and then we have RMC on the y-axis, and then we also want to add label. Let's use D, and then we add the legend. Okay, and we see that. So let me draw it. Update it. So we see that this so this is max depth of 15. It's clearly the best one. Okay, now it's back. So this one, this orange one, is the best. And there is a bonus question as well. So the bonus question, will the answer be different if we change the seed for the model? It will not be, I think. So when I checked on my other computer, it wasn't different. So it should be quite fast to check. So remember last time, so here, this is actually, the answer was 15, right? So orange is 15, right? So remove that. And let's run it with a different random state, or maybe not two, but something random. And I will keep a copy. So this will be, so let's say this one is the old one. Now this one below will be the old one, and let me execute this one. So yeah, it should be fast. Okay, and it is still 15, so it hasn't changed. So the answer to the bonus question is it doesn't change, and it shouldn't. If it changes the answer, then we're in trouble. So in this case, our model isn't really stable, and we need to basically we would need to select a model that is more stable, for which, like, yeah, basically we will not want to select the number 15 if on with one seed it shows the best result, and with other seed it shows not the best result. So maybe in this case we will want to select the parameter that shows the same kind of performance no matter what kind of random seed we select. Okay, so let me clean it a bit. So I'll put back 1. And I will remove one of the plots. Here, the answer is no. Okay, so then we have the second question. And this question is about extracting feature importance information from tree-based models. So because when we have a tree-based model, like a decision tree, at each step of our learning algorithm, then we want to find the best split, we calculate impurity, and based on this impurity, we can see like which feature is the best one. And this information is actually available for us. We can use it. So it lives in this feature importances field. And what we can do is we can train a model with these parameters, and then we can see at this feature importances field, and it will tell us which feature is the most important feature according to decision trees, according to random forest. So let me copy. Yeah, I will copy this one. Also, I want to copy the fit, I think. So these are the parameters that we need to use. Let me copy them. Okay, and let's run it. So it was quite fast. So now we have this random forest model, and we can take a look at feature importances. So this one, so it just says, so if we can actually take a look at what it says. So this is impurity-based feature importance. The higher, the more important the feature is. So remember that each time, at each step, when we select the best split, we calculate this impurity, and yeah, so it tells what exactly it is. But basically, the main idea here that the higher this value is, the more important the feature. And so basically now we need to first find out, so for each of these numbers here, what is the corresponding feature? And then we need also to sort it. And for that, let me create a data frame. I'll call it data frame importances. And then the first thing here, the first column will be, let's say, feature. And I will use a dictionary vectorizer, get feature names. And then the second column will be importance. Or I don't know. Yeah, let's call it importance. And let's see what is inside. So this is how our data frame looks like. And what we can do now is we can sort it by importance. And we want the most important one at the top. So ascending is false. And let's just take a look at that. At the three most important features. And for us, the most important feature is the room type. And it's probably not a surprise because we already see this when we train just one tree with just one split. That was also the feature that was used there. And then latitude and longitude seem important here. I don't think they were important in linear models. So when we were training a linear regression model, remember, or logistic regression for predicting the binary price. So these features weren't really important, but here they are. And yeah, these two as well. Okay, and the answer here, so the most important one is this room type entire home apartment. So let me do this. Okay, so that was the last question about random forest. And the next one is we will train an XGBoost model. And here in this question, we only want to tune the eta parameter. So of course, if you want to tune, you can play with other parameters. But for this exercise, we just will tune eta parameter. So first, let's import XGBoost. Okay, we have it. And now we need to train a model. So let me copy these parameters. I think what we need to do next is create the matrix for train and validation. So I'll just open the notebook that we used and copy the code from there. Okay, that is a long notebook. So where do I create the matrix? Yes, this one. So create, I don't think I need to change here anything. Yes. And then we will also need to create this watch list. So let me create it here. And then we need to train a model. So put it here. So train a model with these parameters for 100 rounds. So let's fix the number of rounds. And yeah, let's also do this verbose eval 5. And we see that it prints already prints everything. And then now we have that. We can do the same with 0.1 and 0.01. So let's change this to 1. Execute it. And I'll also do this for 0, 1. Okay, so what we already see that this model, it takes a while for this model with 0.1, 0.01. It takes a while to converge, to have good performance. So even after 100 iterations, it's still above, still only at 1.63 level. So it's just too slow for us. While here we already have 43 and 43. So now we just need to see which one is better. And yeah, so here we see that it never goes to below. So probably the best one is here, this like 0.432. So it's this one. Yeah, it's actually like it's still improving. Like the last one looks like it's the best one, right? And here it doesn't go to this. It doesn't reach this 2, like in the 3rd digit. So this one is slightly better. So if we were to select a model, to select eta based purely on RMSE, so then RMSE of this 0.1 would be better than RMSE of 0.3. But the difference, as we see, is very tiny. So it's just 1 in the 3rd decimal digit. But the answer here would be actually this 0.1 because it leads to the best, meaning lowest RMSE score. That's where, yeah, so this is the answer. I think it will be useful also to look at the plots. So let's do that. I will now take this function that we used. So put it here. So I just want now to look at the plots for this thing. Then what do we do there? We capture parameters, right? So capture output. Then also let's have now a variable scores, which is a dictionary. Now we capture output for 0.3. Then scores for at 0.3 will be this sparse XGBoost output. This one. Then let's capture output here as well. And I will execute this thing here. So this is 0.1 now. And the last one, yeah, well, I don't think we need to do this. So I can just remove it because we already know that it converges very slowly. So for us, it will be interesting to compare these two, 0.1 and 0.3. So let's do that. So plot. So let's first plot this one. So it was number of iteration. I think let me just take a quick look at the data frame we have. I'm not sure it was parsed correctly. Yeah, so here the names are not correct. So I didn't replace so trainer AUC, validation AUC. The right ones, the correct ones would be trainer MSE and validation RMSE. But okay. So number iteration, and then on the y-axis we will have RMSE, even though it says it's AUC, it's not right. And then this is 0.3. Then let's add legend. Let's label 0.1, and then label here 0.3. Now let's see. So what we see here is, so they both achieve the same, approximately the same level of performance. So if we see here, so they are somewhere here, and we saw that the difference between them is really tiny, right? So this orange one, so let me just add legend here. Yeah, so the orange one is at 0.3. And what we see that it converges faster. So it like already after 10 iterations, it is at the same level as the other at 40. So it converges a lot faster, and it reaches the approximately the same performance. So it's slightly worse, tiny little bit worse, but actually it uses fewer trees, right? So it uses only 10 trees. It needs only 10 trees to achieve the same performance as this one for 40 trees. So let's say if RMSE was not the only criteria for selecting the best model, I would actually go with 0.3, because here it's a smaller model, so it will have only 10 trees, right? And it achieves the same performance. And it's smaller here, it means that it will be faster. So when we want to, say, compute the price of, predict the price of an apartment, the response we will have when we put this inside our web service, it will respond 4 times faster than the other model. So maybe for some use cases, it actually matters, and we want to respond faster rather than being more accurate. So again, it will depend. And here in this case, if we care about speed, then higher eta would be preferred. And if we care about performance of this model as in accuracy, like how good this model is, then it's also not clear, because they're actually almost the same. so only a little bit different. So yeah, maybe in real life I would still go with 0.3. Okay, but for this exercise the answer is 0.1 because the performance is slightly better. We actually can see this if we zoom in. So let's say xlim will be somewhere between 0.5 and 0.4. I don't know. Yeah, so this is it's actually whiling, right? Looks strange. Should be 0.4, 0.5 maybe. Yeah, this way. So we see that at some point actually, so maybe like let's look 0. This and 42 here, 45, 43, 45. Yeah, so we see the x limit is perhaps between 40 and maybe. So we see that at some point, actually the 0.1 becomes better and it increases, still decreases, sorry. And let's look at 100. So, and this one is overfitting. So it is going up and this one keeps going down. So if we really look very closely, then we see that eta with 0.1 is better. Okay, I think that's it for this homework. So thanks for watching. If you have any questions, please ask in Slack and enjoy working on your project. Goodbye.